Okay, so now let's look at capacitors in series. Okay, so again, this was what we just did, capacitors in parallel, where they all added up to make a giant capacitor. All right, well, I have a feeling something will be different if we connect capacitors in series. And what we find out, unlike resistors, when you put capacitors in series, the total capacitance actually diminishes, it gets lower. Okay, whereas this added up, for some reason, this gets lower. Okay, so the total capacitance, if I make a circuit with capacitors in series, it's not the sum. It is the sum of, oh, look at this. This looks similar to parallel resistors, but for capacitors, it's different. For series, it looks like this inverted 1 over C1 plus 1 over C2 plus 1 over C3, okay, gives me my total capacitance. So here, the capacitance of my parallel circuit of capacitors is 62 microfarads, where you put the same things in series, and now they become smaller than the individual components, because 1 over 12 plus 1 over 20 plus 1 over 30 becomes 6 microfarads. Okay, so a big idea to remember is when you're dealing with capacitors, things are kind of inverted compared to resistors, and capacitors in series decrease the total capacitance, and capacitance in parallel are summative. They add it all together. So why does that occur? Well, capacitors in parallel, when I apply a voltage, the voltage is the same across each capacitor. But when I apply a voltage onto a series of capacitors, the voltage is split out. Okay, it's no longer 10 volts per capacitor. The voltage is split out amongst them. So each capacitor has a different voltage applied. Okay, it's divided out. Okay, in this case, I have 5 volts here, 3 volts here, and 2 volts here. Well, how can we calculate that? How do we know it's 5 volts, 3 volts, and 2 volts? Well, I'm going to give you some rules. Okay, so it's important to know that the total charge on each capacitor is actually the same. That's what's written here, Q, Q, Q. So in the end, the total charge, regardless of the capacitance being different, the total charge on each capacitor is the same. And what that charge is, if you've read SOCOS, is that charge on each capacitor is equal to Q total. So whatever you calculate as your total charge due to this relationship from the capacitance, each of these carries that total charge. That's kind of weird, but they all have the same total charge. All right, so let's take a look at that a little bit more carefully. So to calculate your total charge, all right, I'll write that out again. Okay, it's equal to Q on each capacitor, and the Q total, okay, is Q1, Q2, Q3, but to calculate that Q total, you need the capacitance total times the voltage total. So what was the capacitance total? We calculated as 6 microfarads. But to go back up here to calculate that, you would do 1 over 12 plus 1 over 20 plus 1 over 30, and that would give you 6 microfarads. So 6 microfarads times 10 volts, my Q total is 60 microcoulombs. And 60 microcoulombs is going to be the charge on each of these capacitors, which is kind of strange, but true. So 60 microcoulombs is on each capacitor, and each capacitor has that capacitance. Knowing that, I can calculate the voltage across each capacitor. Q total, 60, divided by the capacitance of each capacitor. C1 is 12. So if I divide that, that gives me 5 volts, 3 volts, 2 volts. And they better add up. 5 plus 3 is 8, plus 2 is 10, 10. Okay, so that adds up. 10 volts is distributed amongst these capacitors. Okay, and that's essentially how you solve the voltages across capacitors, the charge across series capacitors, and the total capacitance. You have to be able to work with that.